Oof, okay, finally, I'm going to go over question 7, and this is just a mini-max problem with alpha beta pruning. And so it basically says we want to know the values for these nodes computed without pruning. And then after that, we also want to figure out which edges would be pruned. And so the trick to this, which is a little different than normal, is that the top node is a minimizing node, whereas usually in this class, you've probably seen them with the maximizer at the top. But it doesn't actually fundamentally change the way that minimax or alpha beta pruning works. It's just a little different than what you probably practiced. But yeah, so this is what the problem looks like. I've actually pasted everything onto one page to make it a little easier to look at. But let's go ahead and first figure out these values without the pruning. So I'll start sort of from left to right. We see that we're actually going in post order, if you're curious. So looking at this sort of leaf minimizer, we see that it's going to pick the smaller value between 10 and 5. So this is going to be 5. I wonder, I think, is there an easier way to wipe this out? Okay, 5 goes here. Actually, sorry, I've changed my mind. We're going to put just next to it 5. The smallest of these 3 values this minimizer is choosing from is 1. The maximizer here will pick 5 between 5 and 1, right? And then we need to keep evaluating children here to figure this out. Here, the maximizer is going to pick 16. And the minimizer between 16 and 11 will pick 11. The minimizer here will pick 2. And the maximizer here is going to pick 11. And so all in all, the minimizer at the top will pick 5. And so I won't actually bother filling in this chart, but the way it works, right, is that you put A is 5, node B or triangle B has a value of 5, and so on and so forth. And so that's how you do the solutions for 7A. And now the actual tricky part is figuring out what gets pruned. And so there are different ways we could approach this. I will try to do them both. So the first one is just sort of logicking it out and figuring out what would the minimizers and maximizers each want to do respectively. The second way is to actually write out alpha and beta. And so I'll show you what both of those look like. So at first, we're going to start right here. And at this point, we don't know anything. We can't prune anything because we don't know anything. So we're going to keep going down. We don't know anything still. We keep going down. And then we reach this minimizer. And now we still don't know what our options are. But I'm going to look and I see, oh, as a minimizer, I can get either 10 or 5. And I'm going to go for 5. So the value here is 5. Now, the maximizer here knows I can get at least a value of 5, right? So I'm only going to pick whatever's here if it's potentially greater than 5. So I know as a maximizer, if I go left, I'm getting at least a 5. We keep evaluating here, going in that same post order. And we see E is looking at its children. And E goes, okay, I see a 4. So I can get no greater than 4, right? As the minimizer, I want the smallest value possible. And right now I see a 4, which means if I go for anything else, it's got to be something that's less than 4, right? Because I'm the minimizer. I want small things. But now here's where we see this sort of like incongruency where this says, oh, my value must be less than 4, right? E knows my value is going to be less than 4 or less than or equal to 4. But B knows my value's got to be greater than or equal to 5 because I'm a maximizer, right? If I can pick this going left and get a value of 5, why would I ever choose anything coming from this node where I know the value must be less than or equal to 4? And so as soon as I see this 4, and I know the minimizer is not going to go any lower than that, I don't need to bother checking out J and K, these edges, because I know that this doesn't line up, right? If B must be greater than 5 and E must be less than 4, or sorry, greater than equal to, less than or equal to, whatever, then B is never going to choose whatever's here. And so I don't need to bother looking at everything else. And so we get to prune J and K. So I will just write that down. Great, so far so good. Then we keep going. And so now we reach the top where A as the minimizer says, hey, okay, all I know so far is that if I go left, I can get a value of 5. So my value, because I'm a minimizer, has to be something less than or equal to 5, right? And all of these are less than or equal to, or greater than or equal to. Because again, as emphasizing this, A is a minimizer. It knows now the value of the left child is 5. And so A is going to pick 5, or if anything on the right happens to be less, it'll go with the less on the smaller value. So A's value is capped at most 5. A knows, oh, this is the worst I could possibly do. I'm not going to get any bigger than 5. Thank God, because I'm a minimizer. So knowing this, now let's go back down to the right child, C. And we don't really have any guarantees here, right? All we know is that my parent could choose less than or equal to 5, but I don't know what my children's options are yet. So we keep going, and then we see H. And so H says, okay, my values gotta be, once we see this, H says, oh, my value must be greater than or equal to 10, right? And so H sits there and it knows this, but let's think about what this means in terms of our parent, right? So if H's value is greater than or equal to 10, and the minimizer here must then pick something that is going to be like coming from its two children. If the value here, we know that this value basically is not very good because the minimizer up top is not going to go for it, right? Like the minimizer says, oh, I can pick something that's less than or equal to 5. So nothing that comes from this node could possibly really make its way up. And so we're able to prune this because the minimizer up top is saying, oh, I'm not going to pick anything that's like greater than 5, right? I'm a minimizer. I know I can get 5 if I go left. And so nothing that really comes out of this node matters here. And so we're able to prune Q. Okay. And so now F knows, hey, I've got one child that has to have a value that's 10. And so at the very worst, I'm not going any worse than 10. Okay. But is it possible I do better? Do I have a smaller child? And so we look at the right, but we don't. It's 11. And so overall, the value of F is 10. Okay. Which means this whole child, once we get up here, knows, oh, I can get at least 10, right? Because I'm a maximizer. So my value is definitely going to be greater than or equal to 10. I'm only going to pick whatever comes here if it's bigger than 10 because I'm a maximizer and I want big values. At the very minimum, I'm getting 10. But again, we see that this is not consistent with further up because A says, I'm only going to pick things that are less than or equal to 5. And so we realize this whole thing is a no-go. And so we don't need to bother looking now at any of this child because we realize C is going to be at least a 10 and A would never pick it then because A can pick 5. And so we prune F, and in the process, that means we also prune all of its subchildren because we don't get those either. So F, N, and O all get pruned. And this is that entire problem. And I'm double checking my answer with the solution. I guess the solution doesn't include N and O, which I guess makes sense because they're not directly pruned. They're just sort of like pruned implicitly because we don't bother doing this whole subtree. But so I guess, my bad, these should not actually be marked. Either way, you get the idea. That is problem 7. I will now very briefly do the version where you actually write out alpha and beta. But as a fair warning, I don't like this method quite as much, just because it's a little more tedious. And so you can stick around and watch it if this is how you prefer it, but just a heads up that it does go kind of slow. So as always, alpha starts as negative infinity and beta starts as infinity, and we don't know the value here. We pass these down to our child. And remember, alpha represents the best thing for the maximizer along the route. Beta is the best thing for the minimizer along the path from this current node to the root. So far, we don't know anything. And then we reach this node, right? And so as soon as we see the 10, we know, oh, well, now this minimizer can get a 10, right? And then we see the 5 and we update again, because now we know, oh, the minimizer can get a 5, and that's better than 10. We only prune if alpha is greater than beta, which is not true right now. And so we're sort of done looking at here. We go back up, and now as the maximizer, what do I know? Well, I can get at least a 5. And so the best thing I can do is 5, and that's alpha now, because we're looking from the maximizer's perspective, and alpha is the best thing the maximizer can get. We pass this on to our children, and so we get alpha equals 5 and beta equals infinity. And then we're going to update again. And so as soon as I see 4, what do I know? Well, as the minimizer, now the best thing I can do is 4, not infinity, because 4 is less than infinity, right? And so beta is 4. But instantly we see alpha is greater than beta now. And so we're going to prune these two. Cool. And so this all happens. The value for alpha here doesn't change because we didn't like the values over here, right? And then we go back up. And so now once we've returned up here and we see the value here was 5, the minimizer now knows, oh, well, I'm the minimizer. Beta is the best thing I can do on the path to the root. We're at the root right now. And so beta is 5. Then I pass these values on to my children. We keep going, keep going. And so now I am a maximizer, right? And I see, okay, what can I do? Well, I can get a 10, right? That's better than negative infinity. So I update alpha, and alpha is now 10. But again, we notice, oh, alpha is greater than beta now, which means it's time to prune, because we always prune when alpha is greater than beta. So far, so good. And so we come back up to this level. And now the minimizer is saying, okay, well, the best I could still do is 5, right? The best option that the root knows of, or on this whole path to the root, is 5 if the root just chooses to go left. And nothing here updates that, right? Because that doesn't change as the minimizer, the best thing I can do. I'm a minimizer, and this didn't change my best option because it was big. And then I look at my other value, which is an 11. And again, that doesn't help my options here because I'm a minimizer. And this means beta is not getting updated because 11 is not smaller than 5. Okay, so we come up here, and the value of this whole thing then we determined was a 10. And so as a maximizer, now I know, oh, the best thing I know of on this path to the root is that I could get a 10 if I go left, right? And so as the maximizer, I update alpha, which is the best I can do, and that's 10. But again, we see alpha is greater than beta. And so we prune. And that is how we get that we prune F. And so this is the alpha beta, like writing them down approach. I actually don't know why I was saying I didn't like it, because that went pretty smoothly. I've changed my mind now. Writing alpha and beta out is the way to go. But yeah, that is all of this exam. That was very mentally tiring for me to do. And so I applaud you for taking this exam as a student. Good luck with the rest of the class and have a good rest of your day.